In this presentation, I'll be explaining 555 Astable Multivibrator frequency of oscillation calculation. Previous presentation, I have explained the working of Astable Multivibrator. In this one, how you can calculate the frequency of oscillation of a 555 Astable Multivibrator. In the last presentation, I have explained already the working of Astable Multivibrator using 555 IC. And in that one, again, just as a refreshing that one, here the connection diagram, here there will be two resistances RA, RB, they are connected series to the capacitor, and this RA is connected to pin number 7, discharge pin, and pin number threshold pin, pin number 6, RB is connected between 7 and 6, and 6 and 2 trigger pin and the threshold pin is shorted, and that is connected through the ground through a capacitor C. So these are externally connecting this much only, RA, RB and C. And here the working is as we have seen here, the capacitor will be charging through RA and RB with a time constant RA plus RB into C. And during the charging process, that capacitor is charging from 1/3 VCC to 2/3 VCC. And during that charging period, here output will become high, or here it will become 0, or this will become 0 means Q bar 0, or Q will become high, or here set pin is high here. That is why output is high, or Q bar is low, or output Q bar is low means is an inverter, output is high. That is during 1/3 VCC to 2/3 VCC. That is the charging of the capacitor through RA and RB with a time constant RA plus RB into C. And once the voltage reaches to 2/3 VCC at this point here, here it will become changing to high. Then reset is happening, or Q equal to 0, or Q bar will come high, or output is changing to 0. That is, after 2/3 VCC, the output is changing to 0. And then discharging of the capacitor taking place through RB, because this transistor is getting turned off, and through the capacitor is discharging through RB and through the transistor to the ground with a time constant RB into C. That is discharging from 2/3 VCC to 1/3 VCC. And once this voltage, capacitor voltage is just going less than 1/3 VCC, again this is changing to high, or set pin is high, or Q is high, or Q bar is low, or output is changing to 1. That is transistor getting turned off also. Therefore, then again this is changing from this point, output is changing to high. Then the charging process happens through again RA and through RA and RB, and 1/3 VCC to 2/3 VCC. Therefore, this is the voltage across the capacitor. This is the charging process from 1/3 VCC to 2/3 VCC. During that period, output is high, and when discharging period with a time constant RB into C from 2/3 VCC to 1/3 VCC, during that period, output is equal to low. Therefore, that is the way it is working. You are getting a output at the pin number 3 with a variable on period, or high period and low period. That is, during the charging period high, and during the discharge period it is low. Charging time constant equal to RA plus RB into C, and discharging time constant equal to RB into C. Now let us see the calculation of the frequency of oscillation of astable multivibrator. We have seen here when capacitor voltage is changing from, that is the charging process, from 1/3 VCC to 2/3 VCC, you are getting a high output, or that is represented as T high, the time duration which high. And from when voltage, capacitor voltage is discharging from 2/3 VCC to 1/3 VCC, output voltage equal to, or that is equal to T low, or T low plus T high is the total time period. That will be repeating this one. Now you have to derive what is the time this T high as well as T low, and addition of T high T low will be the total time period, capital T, and 1/T will give the frequency. Now first we have to calculate what is this duration for which the output is high. Therefore, in order to calculate that one, first you are calculating what is the equation for the capacitor voltage at any instant. Therefore, capacitor voltage at any instant is during the charging is equal to Vc equal to, the charging is from the VCC into 1 minus e raised to minus T divided by, the charging is through RA and RB, minus T divided by RA plus RB into C. For RA plus RB into C is the time constant. Therefore, this is the equation of the equation for the capacitor voltage at any time during the charging process. VCC into 1 minus e raised to minus T divided by RA plus RB into C. Now let us take T1 is the time of duration for the circuit to change from to change the VCC from 0 to 2 by 3 VCC. That is not from 1 by 3 VCC. We are calculating from the 0 to 2 by 3 VCC. What is the time? Then you'll be calculating from 0 to 1 by 3 VCC. What is the time? Then you'll be subtracting this time. Then you'll be getting what is 1 by 3 VCC to 2 by 3 VCC. How much time? Therefore, to change the capacitor voltage from 0 to 2 by 3 VCC, then substituting this one in the equation, we'll be getting VC equal to 2 by 3 VCC equal to VCC into 1 minus e to the power of, we are defining as time t1, e to the power of minus t1 divided by Ra plus Rb into C. Now cancelling VC in both sides, and you will be getting one here if you take to that other side, subtracting that one, we'll be getting e raised to minus t1 divided by Ra plus Rb into C equal to 1 by 3. Or that indicates that if you take it is e raised to t1 divided by Ra plus Rb into C, that is equal to 3. Or t1 equal to Ra plus Rb into C into natural logarithm of 3. Or t1 equal to Ra plus Rb into C into natural logarithm of 3. Natural logarithm of 3 you are substituting, and they'll be getting 1.09 Ra plus Rb into C. Therefore, this is the time required to change the capacitor voltage from 0 to 2 by 3 VCC. 1.09 Ra plus Rb into C. Now, again we are going to calculate what is the time required to change from the capacitor voltage 0 to 1 by 3 VCC. Then substituting in the same equation 1, Vc equal to 1 by 3 VCC equal to VCC into 1 minus e raised to minus corresponding time we put it as T2 minus T2 divided by Ra plus Rb into C, or e raised to minus T2 divided by Ra plus Rb into C equal to, substituting it equal to 2 by 3, or e to the power of T2 divided by Ra plus Rb into C, that's equal to it is equal to 3 by 2. Then you'll be calculating what is the time. T2 is equal to Ra plus Rb into C into natural logarithm of 3 by 2, or you'll be getting 0.405, that is natural logarithm 3 by 2 into Ra plus Rb into C. Therefore, this is the time, that is time for changing the capacitor voltage from 0 to 1 by 3 VCC. And this is the time for the capacitor voltage to change from 0 to 2 by 3 VCC. Therefore, the time to required for the capacitor voltage to change from 1 by 3 VCC to 2 by 3 VCC is the difference of this sequence. That is 2 minus 1 will give the time required for the capacitor voltage to change from 1 by 3 VCC to 2 by 3 VCC. That is here. That is T high is that duration. T high is the time to change the capacitor voltage from 1 by 3 VCC to 2 by 3 VCC. That is equal to the first time, that is T2 minus, or T1, sorry, here T1, that is equation 2. T1 minus T2, that is equation 3. That is T1 minus T2. We'll be subtracting this equation 2 minus 3. Then we'll be getting 2 minus mean 1.09 Ra plus Rb into C minus 0.405 Ra plus Rb into C, or you'll be getting 0.69 Ra plus Rb into C. Therefore, that's the equation 4. Therefore, the time duration for the high period, that is this period, T high, that is derived as 0.69 Ra plus Rb into C. Therefore, this is a charging period. That is why Ra and Rb will be coming, or this is a time charging time constant is given by Ra plus Rb into C, and the duration T high is given by 0.69 Ra plus Rb into C. That is the equation 4. That is, this duration is given by this equation. Continuing the frequency of oscillation calculation of an astable multivibrator. Again, the last slide we calculated the equation, or we derived the equation for the duration T high. This period we have derived the equation. Next, you have to calculate what is this duration, that is T low. In order to calculate the T low, we can see that when the capacitor voltage is changing, or the discharging from 2 by 3 VCC to 1 by 3 VCC. How much is this duration? And that can be obtained again from the equation, that is the output of is low when capacitor discharges from 2 by 3 VCC to 1 by 3 VCC. Or substituting the equation for the discharge equation. Discharge equation is given by Vc equal to whatever that initial voltage into e raised to minus t by corresponding time constant R into C. Here the voltage is reaching to 1 by 3 VCC. Therefore, that 1 by 3 VCC equal to starting voltage equal to 2 by 3 VCC. Therefore, 2 by 3 VCC into e to the power of whatever that time minus t by discharging is through RB. Therefore, that time constant equal to RB into C. minus T divided by RB into C. Now you'll be cancelling VCC and VCC, or you'll be getting e raised to minus T into RB into C equal to 1 by 2, or e raised to T by RB into C equal to 2, or T equal to RB into C into natural logarithm of 2. T equal to RB into C into natural logarithm of 2, or that is equal to 0.69 RB into C. Therefore, this duration, the duration for which the output is low, T low is given by 0.69 RB into C. Already T low is 0.69 RB. Already we have calculated, but the T high calculated in the previous slide, and we have that is given as 0.69 RA plus RB into C. Therefore, this is the duration for high period of output, that is T high, and this is T low. Therefore, the total time period is equal to T high plus T low, which is equal to 0.69 RA plus RB into C. This is the charging process, and discharging plus 0.69 RB into C. Or adding these two things, we'll be getting it is equal to 0.69 RA plus 2 times RB, 2 RB into C. Therefore, the total time period, that is total time period means T high plus T low. This is the total time period that is given by 0.69 RA plus 2 RB into C. Or once we calculate the total time period, output frequency is given by F equal to 1 by T, F equal to 1 by T, which is equal to 1 by 0.69 RA plus 2 RB into C, or 1 by 0.69 equal to 1.45, or 1.45 divided by RA plus 2 RB into C. Therefore, the astable multivibrator output frequency is equal to 1.45 divided by RA plus 2 RB into C. That is the output frequency. That is on period plus off period is or T high plus T low is calculated, and that gives the total time period. 1 by total time period is the frequency, which is equal to 1.45 divided by RA plus 2 RB into C. Now let us see what is meant by the duty cycle, a stable multivibrator duty cycle. Duty cycle, or D of a circuit, is defined as the ratio of the on period to the total time period, T on divided by T, that is, or T high divided by total T. That ratio is called as duty cycle. Now here T high is given by 0.69 RA plus RB into C, and T low is given by 0.69 RB into C, and the total time period is given by summation of T high plus T low, which is equal to 0.69 RA plus 2 times RB into C. Now, as per this definition, duty ratio equal to T high divided by T, or T high divided by T means 0.69 RA plus RB into C divided by 0.69 RA plus 2 RB into C. That is 0.69 RA plus RB into C, 0.69 RA plus 2 RB into C, expressed as a percentage into 100. Therefore, this is the percentage of duty cycle, and you can see that one, it is equal to RA plus RB divided by RA plus 2 RB into 100. RA plus RB divided by RA plus 2 RB into 100. Therefore, this is the duty cycle of this astable multivibrator, which is the ratio of the T high divided by total time period, or sometimes we call it on period divided by the total time period, expressed as a percentage. Now, looking from this equation, you can see that one, whatever the always this T high equal to 0.69 RA plus 0.69 RB into C, or T low equal to 0.69 RB into C, meaning that T high is always more than T low. That is, always T high is more than T low. Because of that one, you can get a duty cycle more than 50% by this circuit. You cannot get a duty cycle less than 50% by this circuit. The maximum possible is the 50%. Therefore, since the T high is always more than T low, because T high is given by 0.69 RA into C plus 0.69 RB into C, but T low is equal to 0.69 RB into C. Of course, T high is more because 0.69 RA is added with this. So for T high will be always more than T low. Since T high is always more than T low, duty cycle will be always more than 50% in this particular circuit. Always in this circuit, always you will be getting a duty cycle more than 50%. And if you consider that worst case, it's not possible actually. If you make RA equal to 0, if you make RA equal to 0, mean that if you are shorting this one, this resistance you are shorting, so that RA is made 0, then we'll be getting R equals 0 means RB by 2RB into 100 or 1 by 2 into 100, 50%. That is, you'll be, if you make R equals 0, you'll get a 50% duty cycle. But the problem is that because since you are shorting this point, VCC will be directly coming to this transistor, and when transistor is on, and that will be causing to damage this transistor. Internal transistor gets damaged if you are directly connecting this point to the VCC. Therefore, that is not recommended. This cannot be done since the collector of the discharge transistor directly connected to the VCC, and this might damage the discharge. This is called the discharge. During discharging, there will be current through the transistor. Since the discharge transistor that is connected directly to the VCC in the absence of RA, or if you are shorting this one, that will be causing damage to this this transistor. Therefore, that is not at all recommended. Anyway, by this circuit, you can get a duty cycle which is equal to T high divided by T. Maximum duty cycle, you can get a duty cycle in between more than 50% or 50 to 100% is only possible. But this circuit cannot get a duty cycle less than 50%. By this arrangement, you cannot get a duty cycle less than 50%. In the previous slide, I told you, you cannot get a duty cycle less than 50% with that circuit. But certain modification of the circuit, then in this one, that is 555 stable, to achieve any duty cycle, what the modification is that you are connecting a diode across this RB. You are connecting a diode across RB, meaning that charging is through RA only. It does not pass through the RB. During the charging of this capacitor, that is taking place here through RA only. Through RA, that capacitor gets charged from VCC through RA, and then through this diode, and through C it is charging that one. So that equation, the charging equation or T high equation is equal to, in the previously we have seen it is equal to 0.69 RA plus RB into C. But in this case, since the current is flowing only through RA, that equation, the charging or T high equation now changes to 0.69 RA into C. That is 0.69 RA into C, because that is bypassing this RB during the charging. That is done by diode like this one. And during discharging of this capacitor, that is once the voltage is reaching to 2 by 3 VCC, the capacitor starts to discharge, and the capacitor discharging is through the RB and through the internal transistor, etc. Already I explained. Therefore, discharging is through RB only, and as the previous case only. Therefore, the discharging equation or T high, during the discharging of the capacitor, output is low. Therefore, T low equal to V is equal T low equal 0.69 RB into C, or T low equal to 0.69 RB into C. Therefore, the charging is through RA alone and discharging is through RB alone. So that this equation T high equal to 0.69 RA into C, T low equal to 0.69 RB into C. Therefore, the total time period T low plus T high, which is equal to 0.69 RA into C plus 0.69 RB into C, or 0.69 RA plus RB into C. Therefore, in this, as per this equation, the duty cycle can be written as T high divided by T, or 0.69 RA into C divided by 0.69 RA plus RB into C, or it is equal to here 0.69 RA into C divided by 0.69 RA plus RB into C, and 69 cancels, C cancels, or RA divided by RA plus RB. Therefore, by this setup, you can have, by properly selecting these values of RA and RB, you can get any duty cycle between, of course, here from the low value of the duty cycle is possible, maybe 10% is possible, 20% is possible, 30%, even 50 or more than 50%. Any duty cycle or percentage wise, that is possible by suitably selecting this RA, RB and RC, and this is possible by shunting this RB by through a diode like this one. Therefore, if you see, this is the equation for this one, 0.69 RA plus RB into C, and the corresponding frequency equation is given by 1 by T, which is equal to 1 by 0.69 RA plus RB into C, or frequency of oscillation is given by 1.45 into RA plus RB into C. Therefore, this is a modification of the astable multivibrator. Only change is that charging is done only through RA. It does not pass through RB. So that equation is reduced to, previously equation was 0.69 RA plus RB into C. But now it is 0.69 RA into C. And similarly, discharging is only through RB, 0.69 RB into C, The total time period we calculated, frequency equal to 1.45 Ra plus Rb into C, and the duty cycle equal to as T high divided by total time period, which is equal to Ra divided by Ra plus Rb. By properly selecting these values of these resistances Ra and Rb, or by controlling these values, you can get any duty cycle, or you can have any duty cycle like less than 50% or more than 50% by properly selecting these values of charging resistances like Ra and Rb. Therefore, any duty cycle can be achieved by this certain slight modification of the astable circuit. Only thing is that a diode is bypassed by passing this resistance Rb. All other parties are same.